Okay, so yeah, this is the third lecture, so I try to finish today with what I wanted to say. I wanted to discuss two things. I want to finish discussing the general context of dual integer circuits, and in the second part of today's lecture, I want to say a little bit of how to approach the problem of level statistics, which is one of the more challenging ones. And try to argue why I think level statistics is still interesting to discuss in the context of many body physics. It's not so clear. So we have introduced yesterday the double gate, right? The folded gate, which acts directly on the space of operators, and this gate satisfies four different identities. I just remind you by writing them again here. So it's either unitarity or unitarity and trace preservation if you want. So you try to contract from the top, and or you can contract from the sides. So this would refer to as sideways unitarity, and all these properties together we would refer to as dual unitarity. Okay, so these were the four properties we had yesterday. And then we would like to contract circuits, right? And correlation functions, for example, and I will not try to complicate things by trying to write general proofs. It's not hard, but in this case it's so obvious and trivial that I will just present the result, right? So suppose you put, so this is like a fabric of space-time, right? You put a circuit, which is, if you want, yeah.
I think you have to swap the right-hand sides in 3 and 4.
I want to swap the right-hand sides. 3 and 4.
No, I guess this is correct.
Yes.
You just imagine you make these bullets, and then these bullets are pushed through. But there always has to be free ends on the same side.
Yeah,
right?
so
because these guys are like a machine which is like a, cutting grass, right? So it just goes and cuts. But it has to go to the same direction and try to cut as much as it can. Okay. I'm just sketching. So now this is the initial status in the bottom, initial operator. Now I will decide again enumeration like always. So this will be like odd sides, and this will be like even sides. So it's important now to understand that there is a parity, there is this parity of Steganovich effect, right? That odd sides behave differently than even sides. So if you place operator on the odd side, so okay, I will place it on this odd side just to make it more general. And everywhere else I will put identity. And then the only way that, and then I put identity on the top. So I put identity everywhere. And then you see immediately that these identities can be used to push stuff down, right? And it will hit this operator in this way, and this will be 0 because this is a trace of the operator, right? So the only way that this will not happen is if you put a bullet, so another continuous operator. So this is some operator A, and this is some operator B. Okay? So then you will just contract everything here, and everything there, and what you will be left with is this scalar, and that's the correlation function. And it's completely analogous from the other side. Right? So all the other correlation functions are 0. So even if I place the operator not on the right side, let's say I place it on the even side, I can still show that this is 0. Why? It's obvious, right? I use the rule number 3. I have this, and then this is 0. Okay. So the only surviving diagram is this extremal diagram, which sends operator to move this beyond the maximum. Okay, so just summarizing all that, you can write a simple closed form expression for the correlation function. this is, for example, in this case, I would say, okay, now let's define some operator, which is like this, that here it's in and here it's out, right? Operator, it's like a transfer matrix, right? It takes this vector, touches it here, and then what you get, so you take some arbitrary operator here, and then this is again an operator, right? Because it has a free index here, and this free index means row and column, so it's an operator, right? So it's a map which maps operator to an operator from in and out, and this map we will call M plus. And then we define another map, which will do the other way around. So there, of course, are always two versions, right? You can go in this or that direction. So this is M plus and M minus, okay? So you just define this, and what we have just written here, this object is then just traced. We are just practicing, reading diagrams, right, and translating diagrams to formulas. Again, this should be straightforward, right? And what we are doing here is we take this guy, we apply M plus on it, we apply again M plus on it, we apply again M plus on it, and then we apply again M plus on it, and then we take overlap with the P. So what is it? This is M plus 1A, and then multiply P times, P is the time step, and then multiply with the D and take the trace. So that's this object, right? And this will be now the correlation function between A and B from X and Y in time. Okay. Time T is the number of half-time steps, like I defined yesterday. Okay, so now I have the, if you want, the general formula. In general, I have a formula which says that if I move from X to Y in time steps, this is 0 unless I start, for example, if I start this diagram will be non-zero only if I start at odd time, at odd position, right? So I first want to check if position is odd. And then I want to check that y minus x is equal to precisely t. I mean, this is the case here. This is 4 time steps, and x is, let's say, 2. This is 4, so let's say this is 3. And this is 4, 5, 6, 7, 8. 4, 5, 6, 7. Yes, this is 7 position. Yes. So 3 minus 7, 7 minus 3 is 4, so 4 is equal to 4 is equal to 2. Right? So that's this delta function that checks that this is on the light ray, and then this is trace and plus t of it. And then there is another possibility. There is possibility that if we start on the even position, then we have this dependent magnitude diagram, for example. This will be again 4 times steps. This is plus, okay? So this checks, this is 0 or 1, it's 1 if x is even, or 0 otherwise, and this is the other way around, I did before. This is m minus, the way I define it here. Okay, so that's a general formula. So we have completely solved the problem. It's kind of trivial, right? But still, I mean, it's not completely uninteresting, as you will see. So we have a model for which we can compute analytically all two-point functions, so all local operators for all x and t. Okay? And we realize that these correlation functions are 0 unless x minus t, x minus y, so the displacement is plus minus t. So you either move in the direction of, either move the speed of light in plus or minus direction. And there is a very simple intuition behind this. I mean, of course, proof is kind of technicality, which is trivial almost, but there is also a nice intuition about this. I mean, we have a theory which is unitary in space and time. So you can just as well understand this space evolution as dynamics, right? It's a unitary dynamics as well as time evolution. And we understood in the beginning that the consequence of unitarity and local many-body interactions is causality, so that correlations can only be confined in the lifetime, within the lifetime. So what we have now is basically two lifetimes, right? If this is t and this is x, we start here at two lifetimes. Correlations from this point can propagate within this light cone, right? Because they are time causal, but since these dynamics is dual limited, they also have to be we'll make another replica of the same diagram. They are also defined because of this, because I can just reinvent time and call space-time because it's unitary. I also know that correlation should be confined within this cone, right, which is a spatial cone. So the intersection of these two cones is just two lightings. Okay, so that's a kind of naive but nice interpretation of why we can have correlations only of two lightings, right? From this point, we can only propagate this way. I mean, all the rest is zero.
Question.
Yeah.
You said that causality is a consequence of unitarity and locality, but why necessarily unitarity? I mean,
well, we needed unitarity to contract forward backwards. Yeah, you may say, okay, I mean, what I need really is unitarity and phase correlation. Right? I mean, I can do that also for quantum channels. So you're right. I mean, I'm cheating a bit. I mean,
is there such thing as a channel version of this, like dual?
Yeah, there's
not unitarity, dual CTTP, something
yeah,
like that?
yeah, there's a quantum channel of this, and yeah, that's a good question since you asked. There's a quantum channel versions. And this has been a paper by Pavel Kos, who was here yesterday, and some collaborators from Munich, Georgios Styliaris, if I remember correctly, a postdoc from Munich. I'm not sure if I can spell correctly his name, but this was, I think, published. I forgot exactly where, but it's, I think, 22. So yeah, there's a paper. I'm sorry I didn't prepare the reference, but there is immediate straightforward extension to quantum channels. We discuss dual stochastic quantum channels, and the same applies. So unitarity is a bit more over here, but locality is good. Locality is contractibility. Okay, so right, so. So now let's try to understand what these guys really mean, this M plus and M minus. So this M plus and M minus, as I said, are little machines which, process operator and spit out the operator. But these machines are very special. These are the so-called quantum channels. So as I already mentioned, you would, so again for the experts, if I would consider circuits of channels, then this machine would be a channel of channels, right? So it will be no, it's a third channel. Sorry, I exaggerated. So you don't have to follow it again. It's third channel. But anyway, so right. So now, so what I can now do is I can write explicitly, for example, how M plus acts on A. So I can now unvectorize the W. Unvectorizing the W means I take, since what M plus did, I look at M plus, what it did. It took an operator, it tensor multiplied with identity. Then I apply a gate, but now I will unvectorize the gate, so I do it in a Heisenberg picture, right? So I do it forward backward, one time step to the gate, and then I take a partial trace, because this means partial trace with respect to the same space. Okay? And that's exactly what people understand as one of the canonical so-called Stein representations of a quantum channel, of a completely positive trace preserving. So this is completely positive trace preserving. Okay, so I mean, this of course has nice properties. This is sometimes also referred to as a quantum Markov chain, And what we have now basically, what we have shown is that the correlation function has been reduced to a correlation function of a single qubit quantum channel. So to a single qubit quantum Markov chain. So this is like a very nice situation in which we have mapped a many-body interacting system to a simple non-interacting perfect quantum Markov chain. This is an ideal situation. It doesn't happen often, right? But it's something that people may have expected. I mean, that sometimes chaos means that system should act as a perfect Markovian reservoir for each of its constituents, right? This is what happens here, right? You think of a qubit, and if you think of dynamics of a single qubit, then the rest of the system acts as a perfect Markovian bus with respect to this dynamics, right? And this is described by this channel. So correlation functions are simply correlation functions. All right, so now what we can do now, okay, first of all, this channel of course is unital, so it's m plus minus a unital. So this is a special feature. I mean, not every channel which is equal to this form is unital, but these guys are unital. I mean, okay, this is in this form that we have an entity here that is unital. So this guy is unital, which means that it conserves identity. That identity is an eigenoperator of eigenvalue 1. So there's always a trivial eigenoperator of eigenvalue 1. So, so they're going to consider a spectrum. Right? And one can consider, let's call it a Bj, little operator, which has an eigenvalue lambda j. Okay. I will not put indices plus minus here, I'm just thinking of discussing one of those. Right. So now I can consider also, this is put with the right eigenvector, I can consider also the left eigenvector. The left eigenvector is the eigenvector of the conditional joint channel. And this one I can define with a complex conjugate. And then it has a complex conjugate eigenvalue. And I can define these two guys to be biorthogonal. So I just decided that I put complex conjugation here, so biorthogonality now means this property. You know, this is a non-normal matrix. A channel is a non-normal matrix, so it has a left and right eigenvectors. You can have a spectral decomposition in terms of spectrum. You can assume that it's diagonalizable. It doesn't have to be, but you can assume that it's diagonalizable, and then that thing can be written as when there is a spectral decomposition of this channel. Now, this j will go from 0 to d squared minus 1, and I will always understand 0 as a trivial eigenvalue, and the corresponding trivial eigenvector will get.
Shouldn't it be uj times vk?
Uj.
Because you want to be the biorthogonal.
It does not really matter here, right? Yes. So this is.
Yes. Yeah, like the verso, the other way.
Yeah, sorry. So now. This would be like uj would be the right eigenvector. Yeah, if I apply this to uj, I use this property. So this would be m plus minus as a matrix, right? You can always think of writing a matrix of a channel. It's a d squared by d squared dimensional matrix. So you can think of it like a matrix which has eigenvalue 1, which is trivial, in the basis, and then the rest of the matrix is here, and what we are interested in is the spectrum of the non-trivial part of this channel, which is d squared minus 1 by d squared minus 1 dimensional matrix. For example, for qubits, this will be a 3 by 3 matrix. So there will be 3 eigenvectors here. And then what we have basically here is well, yeah, it's a spectral composition of this channel. So then we can discuss maybe the so-called ergodic hierarchy. Ergodic hierarchy. Which would be, I mean, this is again connecting to the standard business in dynamical systems theory. When people discuss ergodic properties of classical dynamical systems, they define similar objects. They can define some sort of transfer operators for observables or classical phase space with the property definition of the space and the measure of this space. They can define operators in a way that they have a spectrum, which is inside unit disk, and correlation functions can be written again with respect to the composition of these operators, and then you can discuss ergodic hierarchy based on whether these operators have eigenvalues within unit disk or still remaining on unit circle. I mean, this is of course, I mean, this means that, you know, that this will be completely different ways of behavior of correlation function, because now what I just wrote here, right? Okay, I will write it. Now, having this, I can write a correlation function, right? Which is trace of d n to the t plus or minus, doesn't matter. Then just put here the label u, and this u is either plus or minus. And then you can write it using the spectral composition. You can write it in this way. This is an eigenvalue to the power t, right? You can just take the tth power and using my orthogonality, Vj dot uk is delta jk, right? That would be the dot product, and these are vectors. This is vectorized, this would be the dot product, Vj dot uk. So that means that taking tth power, we just take tth power of the eigenvalue. Okay, but now applying this to vectors, now this would be like, I mean, now I'm a bit uneasy with notation because I interchangeably think of vectorized notation or operator notation. And if you think of vectorized notation, this looks like B, M, U, T, A, right? You can write it like this. These are vectorized operators, and this is overlap of A with respect to B, and this is overlap of B with respect to U. So what we have is this trace B, U, J, trace A, B, no, this is, yeah, J. But you can put also label to the eigenvector. So maybe it's convenient also to put the label to the eigenvector. So I will just put another label to the eigenvector. Sorry. Okay. Right, so now this is trace B, okay? Right.
So we left out the identity out of the composition because it's traces operators.
Say again.
We left out the identity.
We didn't let it out because J identity is equal to 0.
I see.
Yes. But it's true that identity doesn't contribute to this correlation function if any of these two operators is present, right? Because UG0 or V0 are now are both identities. Okay, by definition, both operators J to 0 to trivial eigenvalue of the identity. So this would mean that this is just trace B or trace A. So this is 0. So that's identity doesn't contribute. Otherwise, there will be a flat part of the correlation function, which is not the case. So, okay, right. So that would be like a trivial aspect of the composition of the correlation function, but it's already interesting enough because you see now everything depends on whether you have a non-trivial eigenvalue, which is on a unit circle or not. Right? Trivial eigenvalue can be taken out. That's for one set, and you can just put here. Sorry, I told you from making a mess here, but I can just put here in brackets. I can also just start with sample 1 because trace A and 0. That means I don't have to care about trivial eigenvalue, but the non-trivial eigenvalue can still be written in a circle, and yeah, that will give us very different degrees of correlation. So now we can discuss different cases, and these different cases are usually referred to as algebraic hierarchy of classical dynamical systems theory. So we can think of them also as a kind of discussion of quantum many-body algebraic hierarchy of doing this. It's a very special, of course, situation where we are able to do that. In general, this is very hard, impossible problem, I guess, but in this situation, we can do it. So that's good. So we have classification, okay, of different cases. So first case, which we would call non-interacting. Now, I mean, everything becomes very simple, right? For qubits, this is a 3 by 3 matrix, or 4 by 4, but one element is trivial, one corner is trivial, so the rest is just 3 by 3 matrix. I have it somewhere erased probably. So everything is just about diagonalizing a 3 by 3 matrix for qubits. For qubits, it's just d squared minus 1 by d squared minus 1 matrix. So now what can happen is that all these remaining eigenvalues are equal to 1. So this will be called non-interacting. So all, and we will discuss an example in each of the classes. So all 2 times d squared minus 1 non-trivial eigenvalues so these are larger or equal to 1 are equal to 1.
But by trivial, you also mean eigenvalue. But by trivial, you also mean eigenvalue 1.
By what?
By trivial eigenvalues, you also refer to.
By trivial, I mean eigenvalue 1. Yes. When I say trivial eigenvalue, I mean eigenvalue 1. Yes. So, yeah, the special eigenvalue 1 which corresponds to eigenoperator identity. So there is one eigenvalue which is always there, which is always there because of conservation of identity. So there's always an invariant state, right? In any discussion of ergodic theory, you always find an invariant state. Invariant state is corresponding to eigenvector of eigenvalue 1, which people refer to as a trivial eigenvector or trivial eigenvalue. So now, when we discuss ergodicity or non-ergodicity, we want to see whether there are additional non-trivial invariant states, which means that if there are additional eigenvalue 1s, and this will come just now, but this is the most trivial situation, which I call non-interacting, is where all the other eigenvalues are also 1. And you immediately see an example. So that means, of course, nothing happens. Right? All these guys are 1, nothing happens, so correlations are flat. All the correlations are flat, so I now try to just sketch what can happen. So C, B, A, Y, X, T, Y, constant. This constant depends on the overlap of these coefficients. So this is C, T. Nothing happens, and that means that the spectrum, I also plot the spectrum, all the eigenvalues are equal. Okay, this is really natural. And an example is this one. So if the gate is just a swap, swap is obviously a dual unitary, right? Swap is unitary, but it's also dual unitary. Swap is this gate, right? So it's only exchanging this direction, but it's also only exchanging in that direction. It cannot do anything. So it's just yeah. So this is a waste of time to discuss it further. So let's try to discuss something more interesting. The next case which can happen is when we have a non-ergodic, that's interacting dynamics. And interacting. That means non-ergodic. I mean, now again, standard criterion of ergodicity is that there should be no additional eigenvalue 1. So if there is an additional eigenvalue 1, system will become non-ergodic. And it's clear why, because there will be additional terms here which will not decay. which means these terms which will be additional will not decay because they will have non-zero coefficients. Because for that terms in generic case, in generic A and B, this will be non-zero because this will not be just trace of A and B, but it will be trace of A and B times some non-zero. Okay, so if there are, for example, there are n where n is larger than 1, but of course smaller than 2 to the d squared minus 1, not all, because it's pretty smaller. Lambda mu j which are equal to 1, meaning that we imply that CA yx will again approach a constant, which is not zero in the limit. So you'll have a picture like this. You have some decay, but then you have a flat plateau probably. That implies that some eigenvalues will be 1, but there will be some eigenvalues inside. So all the eigenvalues, of course, have to be within the unit disk because jam cannot explode, right? It preserves the trace. So if any eigenvalue will be outside unit disk, the corresponding there will be initial condition for which this will explode. This can happen. So, consequence, all the eigenvalues are within unit disk, but they're going in general be inside. Yeah. Okay. So that is non-ergodic, but already non-trivial dynamics. Then there are two more cases to discuss. Case 3, ergodic and non-mixing. There is, in classical ergodic hierarchy, there are two important notions. One is ergodicity, the other is mixing. Mixing means something like ergodicity but stronger. So the system can be still ergodic but not mixing. So mixing means relaxation to equilibrium. So that it could happen that system is ergodic but it doesn't relax to equilibrium. So what can it then do? Well, it can swing around equilibrium. It can perpetually oscillate around equilibrium so that the time average is 0, but the system never really relaxes. So that can happen if there are some eigenvalues which are remaining on unit circle but not at 1. Because eigenvalue which is on unit circle but not in 1, well, that means that here in this sum, this is e to the I5, right? Eigenvalue will be e to the I5. It means that here it would be e to the I5t. It means that it would be a swing or oscillation with some frequency, right? So quasi-periodic oscillation because time is discrete, but things will go around. So that is an ergodic not mixing, so that means that all non-trivial eigenvalues are away from 1, but lambda mu j are different from 1. That means for j larger than 1, but there exists some lambda mu j which is equal to 1 in absolute value. Again, j larger than 1, not trivial 1. Okay? Of course, if there is 1, there has to be a second one because eigenvalues have to come in pairs. Turns out that quantum channel can have spectrum, has a real characteristic polynomial, which is obviously easy to show. So it's kind of time reversal if you want, in a generalized sense. So the spectrum has to be symmetric across the real axis. So what will happen then is correlation functions will show like this. Now this will be, of course, if time will be continuous, but time is discrete, so correlation functions are points which will never decay, but on average will decay. So this will happen if the spectrum will have eigenvalues like this. There will always eigenvalues here, there will be eigenvalues inside. Of course, now I'm exaggerating because there could be at most 4 eigenvalues for quantum channel qubits, but for qubits there could be many, and things can be inside. And then, well, as soon as you have guys on the unit circle, which are not at 1, you will have oscillations, right? I mean, now I just did throw a buzzword because in many body physics, people have reinvented this type of phenomena, well, in different contexts, but still, I mean, in dual unitary context, this could be called time twisting. You could think of this as spontaneous working of time translation environments, right? because the system is time translation invariant, but the correlation function can display some oscillation with the period, which has nothing to do with the period of invariance. So that goes under general time distance. Okay, so the last and the most generic case, sorry for being chaotic, so I'll put it here, is the general case. And of course, these cases are like, this is like a which means the previous case is a special case of a different case. So 1 is more special, 2 is slightly less special, 3 is less special, and 4 is the generic case. Without turning any knobs, you will get the generic case with probability 1. If you just throw the dynamical system at random, you just throw gate at random, which is dual unitary. And this is the so-called categorical mixing case, or you call it also chaotic sometimes, categorical mixing, which means that all eigenvalues, all non-trivial eigenvalues, non-trivial eigenvalues are smaller than 1. Okay, so that means that the correlation functions then decay exponentially. So then this means that there is an eigenvalue, which is, so that means there is a trivial eigenvalue, of course, this is trivial. But then there is a non-trivial one. Let's suppose it's on the real axis. It doesn't have to be. There could be a pair of eigenvalues on an inside complex plane, but let's say that there is a trivial one, like this, and then the rest of the right side. Okay? And there's always the one which is maximally close to the unit circle, but it's not a unit circle, right? But that's a special guy. Because this guy will determine ultimate asymptotic decay of correlations, because that's the guy which will decay slowest. That's the slowest one. We also sometimes we call it slowest counting mode. So if you look at this sum, after a long time, this sum will be dominated by the largest lambda, which is not 1, which is not trivial, because trivial one doesn't contribute. So the largest 1 to power t. So this means that if this is, let's call it lambda 1, if this is lambda 1, then correlation function asymptotically goes like lambda 1, so it's proportional to lambda 1 to t. So it's e to the minus the logarithm 1 of lambda 1 times t. So I just wanted to write it as an exponential decay, right? I mean, it's the same thing. It's just some number smaller than 1 to power t, but you can always write this e to the minus something positive times t, which is positive is logarithm 1. Okay, so now that's the generic situation, and that, you know, what we have shown now in this particular class of systems, perfect chaotic many-body systems, all correlations, all simple correlations of simple operators, local operators, if they decay exponentially. There is nothing more interesting to be expected.
Question.
Yeah.
Where does integrability fit in here? Is it possible? Is it compatible with this or no?
Yes, not with that. Integrability, well, yes and no. I mean, it's a good question, of course. I mean, it's a tricky question, right? So, in general, integrability would fit into category 2, which means there would be so-called charges, which corresponds to eigenvectors of eigenvalue 1. But maybe there are integrable systems for which the lowest charge is already complicated. And if this integrable system would also do a unitary, then it would pretend to be chaotic if you just look at local charges. I don't know of any example, but I can imagine this would be possible. Probably these systems, such system could not be dual unitary, so maybe this example is not really.
But there are examples of dual unitary plus integrable in sense that
yes. Yeah, I will go through, now I will try to discuss a bit of parameterization of this set, and I will go through a list of examples and also integrable cases. So yeah, this is the last thing I wanted to say in general, and then we'll spend maybe another 45 minutes or so discussing spectral statistics. Okay, so, right, so now, so let's try to parameterize the set of the. Okay, so now it looks maybe so far, this is something very special that you should never care about this, right? Because you do not hit on this very intense. Well, it may be true because you have to find two parameters. But it turns out that you don't have to find two so many parameters as you might naively expect. So you just have to find two a little bit. So there, it's still quite possible that you will keep something that's dual unitary, even by, well, not by chance, but almost by chance. So let's try to parameterize first, parameterization of the set of dual unitary gates for qubits. Well, this is, I mean, I will just throw it at you. I mean, this is like, there are two things that one has to observe. There is a simple claim. Yeah, I don't know. I mean, I shouldn't go too much into detail discussing this because it's quite particular. But even though it's important, it's particular. But one claim which probably is worth to think about is if U is dual, then the product of U1, U2, U, V1, V2, where U1, U2, V1, V2 are single qubit, I mean also the qubit, I mean I'm still having generally qubit, this holds for generally, are single qubit gates, unitary gates. Then this guy is also so the proof is obvious, almost obvious, but it's good to sketch it, to think about this. So what we have basically is first U, and here what we have is U, which is decorated by 4 single qubit gates, and single qubit gates are like little balls which transform each wire. This is the which transform each wire just locally, right? So it's unitary, right? Unitary, it has two legs, right? And now, okay, obviously, how do we prove unitarity? Unitarity, of course, is obvious, right? So let's just prove dual unitarity. Dual unitarity means I take, so this is U1, U2, V1, V2, this is U, but now let's take the conjugate, U dagger, and this is now, when you take the conjugate, you also have to transpose, right? Which means that this guy will now come on top. This is U1 dagger, U2 dagger, V1 dagger, V2 dagger, okay? And then we do this. Then we do this, and we do that. Okay, this is one. I will just do one of the things. But what happens now is that we get U2 dagger hitting on U2. So when a gate hits on its Hermitian conjugate, it annihilates it, right? This is unitarity. And V2 dagger hits on V2. It's also unitarity, it annihilates it. But then this is the standard dual unitarity, which means that this is just putting short circuit wires here, right? So now what we have is this and this, where this is V1, U1, sorry, should be the other way around, should be this. Right? This is right? We just forget about this, but still we have to put this wire across this one. Okay? This is U1 dagger, this is V1, and this is V1 dagger. And again, U1 hits on U1 dagger, it annihilates, and V1 hits on V1 dagger, it annihilates. So basically what we have is this. Okay? that's just that was just the first step for of course, we can prove this also by folded, just looking at folded circle. That's maybe more straightforward. So yeah, and then of course you can check the same way the other rule which defines dual unitarity. So clearly, dual unitarity is invariant under local rotations, right? By arbitrary local unitary weights. Fine. That means if you have classified somehow a class of U's, then you can just enrich them by these kind of local decorations, and they still I mean, right, this is an interesting thing to have in mind. But then for qubits, fixing d equal to 2 for qubits, there is a general kind of formula for qubits. U is, of course, a member of unitary group of dimension 4, and there is explicit formula. I mean, there are articles. What the references to the articles from 20 years ago, people who began thinking about quantum information seriously, they came up with the explicit, I mean, this is of course just exercising group theory, but people in quantum info provided explicit parameterizations of U4, which were convenient, and this is also convenient for us. So there is a parameterization of U4, which is like that. We take, again, what I said, arbitrary SU2, arbitrary a single qubit gate, which you can take as an SU2. And then you take a gate which is Heisenberg gate, so-called Heisenberg gate. So it's generated by the Heisenberg, arbitrary anisotropic Heisenberg interaction. And then there is V1 cross V2. And then if you take U1, U2, V1, U2 as SU2, then you have to also put a local place here. Okay? So now we are counting, right? You remember your lessons in group theory, right? The unitary group is parameterized by unit group dimension of UN is parameterized by n squared parameters, right? In this case, it should be 16 parameters. Let's just count. This is SU2s. SU2s are parameterized by 3 Euler angles, right? So 3 plus 3 plus 3 plus 3 is 12, plus 3 is 15, plus 1 is 16. Fine. So it counts correctly, right? So this is the full manifold of 4. Now the question is, what do we have to do with it to make it do it? We can forget about this guy. So this is an exercise which you can do in the brain, in mathematical, you have it on your computer, and it's a very simple exercise. I just showed you that you can forget about these local gates. You can put them afterwards, this decoration at the end. You can just check under what condition this guy in the middle, the Heisenberg gate, is dual. So just swap space and time, and you demand that this guy becomes unitary as well. And what you get is up to, which is unique, up to trivial cyclic permutations. The cyclic permutations are local rotations, right? So I don't use any generality. So asking for this to be dual unitary, if 2 out of 3 Heisenberg coupling parameters are pi over 4. So 2 out of these have to be pi over 4. Right, so which means that we have still 16 minus 2, because we have fixed 2, we have still 14 parameters. So we have still a lot of parameters. We have a manifold in unitary group, which has codimension, which is just 2 constraints. Yeah?
Sorry, where is time now?
Time? There is no time now because this is just a local beam. Now we are discussing what type of Lego we can use to make our circuits, right? And what are the constraints? Because obviously this cannot be arbitrary unitary gate. And what we have found is that there is some constraint, of course, on this interaction. Because this is non-interacting, this is non-interacting, are of course better, but the interaction is constrained. Only 2 of these parameters have to be pi over 4. So now this is actually interesting because it actually can be interpreted more easily. I mean, this gate now, which is pi over 4,
Our question is now where do I get this constraint from?
Where do you get, by asking this to be, by asking the dual of this. So the constraint is by taking the dual here. This means this operation I defined yesterday, which means you swap this, and you, I mean, this is something that you can easily compute, right? It's there's a product of couple of bounding matrices, right? This is a 4x4 matrix. You can put it in Mathematica, you get the answer without any problem. You take a reshuffling of indices, and then you ask it to be united. Again, you're going to get the answer in a few minutes. I mean, it's not a big deal, right? We could also do it by hand, but you know, time is precious.
I really don't remember this two-word transformation. What do you mean by the two?
So we define this transformation, IJKL, which was UIKJL. So now this is a matrix 4x4. This is row, this is column. Yeah. So this was the space-time flip. Okay? You do the space-time flip on this guy, and you ask it to be united. And then you get this solution. And now we look at this a little bit more carefully. So what we get is this fundamental interaction, which is unitary, which looks like the XXZ model. I mean, okay, so this is YY plus some arbitrary J ZZ. And now again, this would be more like for people who have some experience, but you know that this is very close to what people call swapping. I mean, if also JZ would be 5/4, then this would actually generate a pure Heisenberg exchange. I mean, really pure swap. You can write it as a combination. This is an XXZ, so it was part of my first lecture. This is something that generates integrable system, and it's also an answer to the question 10 minutes ago. I mean, this gate can be dual unitary if these two parameters, that is Jx and Jy, is equal. So it's a special case of integrable Heisenberg, anisotropic Heisenberg circuit, XXZ circuit. And if you take one of the coupling constant pi by 4, it becomes a but as I say, I mean, this is also very close to a swap. I mean, it's a small modification of a swap. You can just take out here, you can take Jz as pi over 4 plus j. So Jz will be pi over 4 plus some j, which is some constant, right? And now this becomes up to a phase, which I don't care now. This becomes a swap. I don't know how to write a swap. A permutation times e to the ij sigma z across sigma z. And now the interesting case is if j, this is swap, and if j is equal to minus pi over 4, I mean, maybe I should write it minus j here. I think it's better to write minus j here. Then if j is equal to pi over 4, then this will be my maximally chaotic. If j is equal to 0, this is just swap. If j is pi over 4, this is maximally chaotic. And this case becomes what people in quantum simulation, quantum computation know as I-swap. I-swap is a gate which is very similar to swap, but it has an I somewhere instead of 1. And this I is, well, is the root of this pi over these pi over 4 things here. So, I mean, what is, yeah, this gate is still very simple, but it's kind of maximally chaotic. I mean, provides maximal, we can discuss this for a long time. I try to focus on one thing today, but you know, these gates, I mean, this circuit with J, which is in this case equal to pi over 4, so that means that this is 0, this circuit is maximally intact. It has maximum capacity of correlations.
So swap is sort of non-interactive, but
Yeah.
I swap is maximally.
Yes. Which is that would be crazy, right? Both have equal non-zero elements, right? I instead of 1. Of course, if you decorate stuff with well, I swap in principle is still integral, right? So just I swap gates are integrable, nothing interesting. So you have to decorate them with single qubit stuff, which scrambles things, I mean, which mixes bases in which they are simple, right? And then it makes everything kind of cool. Okay, so now this was like a simple discussion of how you can create your favorite dual circuit, right? Now, yeah. So just to summarize, I will just take summarize. I will take a dual unitary gate, U1 plus U2, and then there will be permutation to the I 5 or 4 J, sorry, I J, sigma Z, sigma Z, and then is E1 plus. So this is, and then it has 3 plus 3. If you want, you can put a global phase. But global phase is really completely irrelevant, right? You take it out. So it's really the non-trivial parameters of 3, 3, 3, 3, and 1. Okay? So if you want, you have whatever certain parameters. Right? It turns out that not all these certain parameters are independent because this one has a U1 symmetry. And that means that you can divide out this U1 symmetry from this SU2s and you get one parameter less in each of the SU2s. Okay, so now you can ask, of course, now this is all that we know basically on parameterized dual unitary gates, right? I mean, this is the only complete result we have from parameterization for qubits. For qubits, we can do it. Now people ask whether we can do it for qubits for d larger than 2. And there is the first answer. We have no idea how to write general classification of dual unitaries. I mean, how to count how many free parameters we have. We have some numerical experiments which suggest some conjectures, but nothing has been really proven. But there has been some proposals. One proposal, which is particularly cute, is to generalize this formula to qubits, and where you can just take, instead of Pauli matrices here, you can take here spin J representation of SU2, and then when you have D, which is 2J plus 1, spin J, here, SU2. And then you replace sigma Z here by SZ in the corresponding here of spin J. And then, of course, here you can then take, in these matrices, then you can take as SU D matrices, where D is 2J plus 1. So this works. So this gives us dual unitary circuit in 2J plus 1 dimension systems. But it's highly incomplete. I mean, it's highly, this doesn't give us all dual unitary circuits being larger than 2. This gives just a nice family, right, which directly generalizes the qubit case. There's another more kind of serious the extension to higher dimensions, which was proposed, as far as I know, by Tomaž, which is the following. Basically, what you can show, there's one little claim, which is easy to show, but I will give it as an exercise, which is the following, which is true for anything. True for anything. Which says that if U is dual unitary, if and only if the composition of permutation and Q, this P is a permutation as we defined it in the first lecture, and then you take a partial transpose, either with respect to first or second space, doesn't matter, either first or second space. This is a partial transpose, right? You know what partial transpose is, I guess, right? Then this guy is unitary. So the statement is U is dual unitary if the composition with a swap has unitary partial transpose. But then this is very cool because then we immediately can find representations of set of dual unitaries by known representations of unitary partial transpose gates. For example, if you take Q bits, then you can take, for example, you take V, which is of the following type. So suppose this is a D by D, right? This is this guy is dimension. So this is a tensor product of two d by d matrices. This is a pure projector, and this is a unitary matrix. Okay. Sorry, this is so I dagger I is. So the claim is this guy is also unitary. This is one way of writing the unitary matrix, right? The claim is this guy is also unitary. It's easy to check. V is also unitary. It's unitary in the big space. The projectors. Its components are unitary. It's like writing components, right? It's like V1, V2, right? This is a d-dimensional matrix of two matrices, right? It's unitary. It's not diagonal if you want. If you take a partial transpose with respect to the first space, it's also unitary. So it's asymmetric. It has a unitary partial transpose. And so by the claim, which I have not shown, but which is trivial to show, as I announced, we can simply compose it with permutation, and then we have a dual unitary matrix. But now let's count how many free parameters we have. So now what we want is to have as many free parameters as possible, right? If you just look at this guy has how many free parameters? There is a single free parameter here, and then there is t square parameters there. I mean, if t is larger than 2, each SUT is again d squared free parameter. So d squared, d squared, d squared. So it's proportional to 4 times d squared free parameters. How much free parameters we have here? Well, here we have d free unitary matrices. So it's d of them, and each one has d squared free parameters. So here we have proportion to d cubed free parameters. Right? So this, I mean, what I claim is this term is much richer, right? So if you are after finding the richest possible parameterization of dual unitaries, this parameterization is nicer, and it's more complete. We believe, actually, based on some numerical experiments, that d cube is actually the right scaling, but probably there still has to be some prefactor on top of what I proposed. It's really very adequate. Yeah, as I said, there is no theorems. Okay, so now this is, yeah, that's all I wanted to say, probably, in general about dual unitary circuits. Now we can compute a lot of stuff about this. And I said, since time is short, I will not be able to do much. But I will just do one thing, which is I will discuss a little bit the question of error statistics. So lecture 3 will be a little bit on spectral statistics, so random matrix spectral statistics. So I guess I was not able to attend John Choker's lecture yesterday, but I guess he told you about a little bit about the spectral form factor, right? So that's good because we don't have to discuss it carefully again, so you know what it is. And we're also happy that he discussed it in the context of flow case systems, which is the same as we have. So we just take it as something that you already know. And we try to discuss spectral form factor for dual unitary circuits. So, we take the spectral form factor, which is one particular measure of spectral correlations or spectral statistics. As you have heard, if you think of a circuit as a big matrix, you can think of its spectrum, right? The so-called Floquet spectrum, the spectrum of quasi-energies. So this is a Floquet spectrum. Of quasi-energies. goes to, let's say, curly n. And for us, curly n is, well, basically is d to the n, right? We have a d-level system, L qubits, so it's exponentially large in the level system. And right, so we have many quasi-energies, and these quasi-energies can be thought of as points of a unit circle, because they are arguments of eigenvalues which are unimodular. So you can think of them as a gas on a unit circle. So gas with periodic boundary conditions, gas in 1D with periodic boundary conditions. And then the question is, I mean, the main question of statistical mechanics, sorry, of random matrix theory is basically translating these questions to statistical mechanics of eigenvalues, right? So thinking of eigenvalues of random matrix as a gas and asking questions about statistical mechanics of this gas, so correlation functions. Now, what people usually do, and more often do, is they look at Hermitian matrices where these eigenvalues are openly line and they have density, which is non-trivial. You've heard of semicircles already and so on. But in flow case systems, the story is simpler because this gas is confined on a circle and there is no preferential point, which means that the density, there's no reason to be inhomogeneous. Density is expected to be constant, flat, right? Density, which you can define as the sum of Pareto functions. And then we put correct normalization to the density, which is this one, 2 pi. So density is from 0 to 2 pi, eigenvalues are from 0 to 2 pi, so I have to multiply by 2 pi over n, this delta function. Well, that's just for convenience, so that the average density from 0 to 2 pi, 1 over 2 pi is 1 by construction, right? Okay, right. So that's density, and we expect it to be locally flat. So that if you look at a large system, you diagonalize large unitary matrix, diagonalize, you look at the spectrum, then density of eigenvalues, you expect it doesn't happen much. But then what you want really is some measure of correlations between eigenvalues, and for that you can introduce a pair correlation function. I will just do this very quickly because we have heard of spectral factor before, but I'm just doing it for completeness very quickly. So then what you do is basically take one point, I mean, you take a density, and then you write density correlation function, right? So now let's say this is some center and difference coordinate, and then you average with respect to the center coordinate on a circle, and then you take a connected correlator, so you subtract the average square. This means that you average over pi. Okay? And this is a two-point function, so this characterizes the correlations, pair correlations of this gas. And then what is spectral form factor? This is definition. It's just a Fourier transform of pair correlation function. It's just a Fourier transform of r theta to the I theta t dt from 0 to 2 pi. And then it's n squared over 2 pi. And this normalization I use for convenience. I mean, this normalization can differ from author to author, from paper to paper. But for us, this will be the right normalization for convenience, as you will see, because once you do that, then you just plug in the definitions. And what you get is what you get, I mean, this is two-line calculation, which is instructive to do, but I will not do it. As I count on you seen this before, but if you haven't, this two-line calculation is very instructive. What you get at the end of the day is a double sum over the eigenvalues. So this double sum over the pairs of eigenvalues into the I phi n minus phi n prime times t minus the delta function at t equals to 0. Now, just one thing which is important to stress, I mean, this is a Fourier transform of a function which is periodic. So Fourier transform only makes sense if the Fourier variable is an integer, right? It's a Fourier analysis of a circle. So t is an integer, time is an integer. It only makes sense that, right? Because we look at integer number of revolutions of our fundamental cycle, right? U is fundamental cycle for brickwork, like 2 years, and we iterate. So then there's, you see, this scaling was kind of convenient, so we basically have no additional factors here. This n square is at the beginning because the time equal to 0 is sum over n squared numbers here, so we have to subtract that in order not to get crazy explosions. But the rest, I mean, we can forget about t equal to 0, we can only think of positive t. And for positive t, this is just double sum, which is, well, just a square of a single sum, which is just a trace. Okay. So that means that specular form factor scale t is just a trace of this U. This is a big matrix, so it's a trace of a big matrix of our t models. And then I will assume that t is larger than 1, so I don't have to care about this delta function. This delta function, this in singularity equal to 0 is important in continuous time. I mean, maybe I don't know. Yeah, but we won't hear from Professor Tayev today because he'll probably speak about something else, but people have investigated also SYK model a lot from the perspective of spectral form factor and spectral statistics. And SYK model is a continuous time model, so it has also interesting physics for short times. And short times, you know, there is consequences of this delta function for continuous times. In discrete times, this is just instantaneous shot, then it decays. Basically, what happens is that we have this, as I already discussed just now, there is this ramp spectral form factor, but then there's this delta function. But in continuous time, basically, you have this kind of behavior. Okay, I mean, this decay and then the ramp behavior, and then I mean, the start is much higher than the plateau because the start is n squared and the plateau, as we see, is n. So, but for discrete time, of course, this story, I mean, this is kind of not so interesting physics, in my opinion. So, if you look at discrete time systems, there's just no decay, there's just immediately the ramp. Okay? This is short time physics, anyway. But now we are interested in this physics, which is going towards long times. So, I mean, some of us really like flow case systems for many reasons, and one of these reasons is also that we don't have problems with short times. Okay, so now that's, this is just a short minutes on, but let me just continue discussing this definition. So this definition still is not so good, because the spectral form factor is known as not psychology. If you take some dynamical system or some random matrix, you compute that, it doesn't make much sense. What one has to do is one has to compute the average spectral form factor value average and take expectation value with respect to some ensemble of systems. So SFF is not self-averaging. And so it is a big issue. It's a big issue, it's an important issue. It's good or bad. I mean, of course, it's bad for calculations, right? So one has to worry about providing conditional averaging. But it's also good because it means the spectral form factor is a very sensitive measure. It's one of the most sensitive measures, and you can decide how much information you want to convolve and throw away, and how much you want to keep and analyze, right? And of course, because also the calculations of spectral form factor, of course, have their own. Maybe they look at distribution of spectral form factor, not only the spectral form factor on average, and so on and so on. Okay, so now in random matrix theory, this spectral form factor can be analytically computed. I will not discuss because time is short, so I want to finish in 15 minutes. I will just quote the result. Of course, in random matrix theory, most of you have heard of random matrices before. And there are different classes of random matrices depending on physical symmetries. The main ones are orthogonal or unitary random matrices, orthogonal class or unitary class of random matrices corresponding to systems with or without time reversal symmetry. For us to make life simpler, we'll take we presume no additional symmetries, not even time reversal. So this means that we have to use the so-called CUE plus circular unitary matrices, circular unitary ensemble of random matrices, which is the same as unitary matrices. So this is unitary matrix with an ensemble is defined with respect to a measure, so with the so-called H measure. Yes.
What is meant by self-averaging?
What is meant by self-averaging? It's a good question. What it means, I mean, just it's quite useful, to try it by yourself. Take a random matrix, compute this object, and plot it. So what you get is something like this, right? Then you take another random matrix, you plot it, you get something completely unrelated. Another. So what you get is an ensemble of points. For each time, you have an ensemble of points. And only when you compute the average, you have an equal result. But the variance is of the same order as the average. So before you do the average, you know nothing about what's going on. So the quantities which have variance, which does not decrease with increasing the system size. I mean, this is something that you might hope that it cures itself by looking at large systems, but it doesn't. So when you do statistical mechanics and go to thermodynamic limit, there are quantities which make sense in thermodynamic limit, even for individual systems. And these are the so-called self-averaging quantities. But this quantity is not self-averaging, which means no matter how large matrix you take, if you look at spectral form factor defined like this, it will not make any sense for individual matrix. It has to be an average. Yes.
Are there computations for the variance of SFF in the CUE?
Yes, yes.
And how does it scale with the size of the matrix?
Well, what is known is that the distribution of SFF is plus 1 in random matrix theory. So by knowing the first moment, which is the SFF itself, you know everything.
Okay.
So then everything is known for the k-point functions. SFF is a 2-point function, and nth moment is a.
And this means that it's Poissonian at a given moment of time, and different moment of times
has different first moments.
Yeah.
Okay. But the full distribution is. Okay, so now let me just give you the result. You see a V for the unitary case. This should be compared to chaotic systems without any special symmetries. So this means you have to average over the whole unitary group with the corresponding measure, which is invariant measure in the group, the unique invariant measure is called H measure, and then we take the spectral form factor, the way we define it, that we average it, right? This is expectation value, and then we get T or N for times long. So what happens is this type of picture, the spectral form factor has a ramp, what we call a ramp, so linear increase, and then this. So it's a very simple behavior, it's a very special time in which it separates. This is the so-called Heisenberg time. I think it was mentioned already in Professor Tomaž's lectures. It's the longest time in quantum dynamics, which makes sense, in a sense, right? Because after that time, you start to resolve individual level spacings, right? This is related to inverse mean level spacing, right? Mean level spacing is 2 pi over n. Inverse mean level spacing is n over 2 pi. Don't forget about 2 pi. It's over n. So after this time, if you would be able to measure signals for times longer than n, then basically you see just quasi-periodic quantum mechanics doesn't have any.
This is a large n result, or is this at finite n?
This is any. This result is actually very crude because it's exactly any. It's not only large n. I mean, for other ensembles, I think results are only nice for large n, but this one is 2. Okay, so right. So now the rest of our discussion, because I have to finish soon, but the rest of my discussion will be then to understand under what condition we can prove that quantum circuit has a linear rank. Because, so now, but before we understand what this rank means, we have to maybe compare it with something that's very different, right? And what is very different is the Poisson's comparison. And Poisson ensemble is something that people usually offer as to as the random matrix ensemble that one has to use for integral systems, even though that's a bit of a debatable suggestion, because integral systems are usually very non-universal, but behave special. I mean, each integral system is quite special in its own way, but still, I mean, you can define level statistics for integral systems, and then there was a conjecture. So there was two conjectures, and again, I think they were mentioned before, but I will just repeat them. There was a conjecture, the so-called Buchiga's conjecture, that chaotic systems should be described by that matrix theory, which means that for chaotic systems you expect this kind of randomness. For integral systems, you think of levels as really uncorrelated levels, right? So there was this one here, right? If this phi would be completely Poisson uncorrelated, you could compute that. This would be like a random walk, right? Sorry, kind of thing was missing. So this means that this would be random from 0 to 2pi, but if you multiply by t, which is integer, you still get a random number from 0 to 2pi, which is uncorrelated. So it means that it's obvious that these things cannot depend on t. And you can just compute that, and this is just adding n random numbers, which are completely uncorrelated, take them modulo square, you get double sum, the only contribution comes from diagonal terms, all diagonal terms are completely cancelled away, so what you get is n, right? And the spectral flat is just n. Okay? And it doesn't get on top. So this would be possible. So you see what the game, the interesting question of this game is to understand if you can show, or why is this a huge difference between, let's say, at times which are not very long, but still not very short. For example, this n is scaling exponentially, well, in this case, d to the n exponentially with the system size. So when you have a many-body system, there is a huge gap between prediction of Poisson ensemble and random matrix theory. So there's a huge gap to kind of characterize, I mean, to show, let's say, signature of quantum chaos, right? And when you have an integral system, you expect Poisson, when you have a quantum system, you expect random matrix, so there's a huge gap. This is the main kind of, I would say, order parameter of quantum chaos to show this gap. If this gap would be observed, it's very hard actually to observe this. People are discussing possible measurements of this form factor. It's very, very hard because you have to have expressions and signals. I mean, this is signal order 1, but this is signal here is on the order d to the minus l. So it's okay, but still, conceptually, this is a very nice tool. And right, so I have to skip many things at this point. So there's one simple exercise which I wanted to do, but there is no time. But there's a simple exercise first to start, to warm up, is to show when you take non-interacting spins. I just throw that. I mean, I just throw it as an exercise. I will not do it, but just take a non-interacting spins. Exercise. Take non-interacting spins. So take u. U will then be just tens of rows of local gates, u1, u2, and uj will be just e to the I, j. But it can take just signals. Just like this. It can just take a longitudinal field, random longitudinal field, right? And then you take this as a random parameter or each average, for example. This will be like a random system, random non-interacting system. For that, we can compute the spectrum. And the spectrum is obvious, right? The spectrum decomposes into product. So eigenvalues, so this product, eigenvalues corresponds to the sum of quasi-energies. So quasi-energy is just the sum of points which are plus minus each. So we can compute spectral form factor. So the exercise is compute spectral form factor. Where we average this result is very simple, very nice. The result is just flat. The result is possible. This is a bit of cheating, so because we don't have time to discuss this anymore, but it's a bit of cheating. Average is like Poisson, but the distribution of the spectrum is not Poisson. The spectrum is very strange. So as I mentioned 5 minutes ago, integral systems are strange, and this is a particular strange integral system, which on average has the same features. It's a generic integral system. The average spectrum factor is Poisson, but the fluctuations of spectrum factor are not Poisson. And it's actually not so easy to get Poisson fluctuations of spectrum factor for integral systems. Okay, that's just yeah.
But how is H10 now distributed?
Yeah, good point. Yeah, FJ can be flat from 0 to pi, let's say. I mean, we want this to be, this quasi energy to be flat. So let's say, let's say flat distribution of FJ. From 0 to pi or 0 to 4 pi, I think. So that you cover the whole interval. Because what you get is basically e to the IH and that's averages, right? You have this type of averages, right? And you want this to be 0 unless, I don't know, prefactor here is 0. Prefactor is 0, then it's 1, complex is 0. Okay, so yeah, I think it's very instructive to do this exercise, just to get the feeling. But let me just now really move to the last part, which I wanted to comment on, is calculation of spectral form factor for dual entry circuits in general. So now, this is like a final calculation that you do, and a final discussion that you do. And of course, I have to show why diagrammatics is useful, right? So I will again show, basically again what I will do, I will write spectral form factor in terms of a big diagram. And then we will discuss how to evaluate this diagram in terms of, again, some sort of transfer matrix, right? We've seen that correlation functions are almost trivial, right? Because the transfer matrix is 1D and it's a simple quantum channel. Now for spectral form factor, this situation is much more involved. We can still compute the spectral form factor analytically, but we have to work much harder. And there's lots of kind of algebra in between, which is needed in order to evaluate our result. But still, there are a couple of things that, since we'll not be able to go to details of calculation, I'll just try to stress the main points. And yeah, I hope okay, so what we will do now is basically we will rewrite again spectral form factor as an average. And this is trace of u to the t. And then this is modulo squared. I write it as a product. And this I can also write it in another way. Trace of u to the t.
Can I ask a question?
Yes.
In case of dual unitary, because there's not a group, there's a question of how do you average over them. So do you average over the whole manifold or some manifold?
Yeah, that's a good question, but the question is also why do you want to average over them? Because the kind of, yes, I mean, of course, you may be interested in some applications where it would be useful to average, but I think in principle the idea is that, you know, dual unitaries are not, are not like random circuits. I mean, they are really, they have nice properties even as individual systems, right?
Mm-hmm.
So sometimes we have to average, and when we define spectral form factor, we will average, but we'll average over just local unitaries, where it's clear about how to average. Local unitaries are still a group. But if you want to average over interactions, or dual unitary interactions, then, yeah, first I don't have a good answer, because as you say, it's not a group. It's not invariant measurement. So you may need average over some parameters, but it's not very relevant. Okay, so now what I will do now is I will show I will write the diagram. Okay, so as you see, and then we'll discuss this further. So basically, what we'll do now is basically write two traces. I mean, the spectral form factor is a two replica object. So we have two traces, And yeah, and then we average over the product, right? So it's it's 2-point function, right? So now let me try to write these two things together. So let me just take an example. Time with 2 slices. This will be 1 slice. Second slice. 1, 2, 3, 4, 1, 2, 3, 4. This. Okay, and then and now we will assume periodic boundary conditions, and we assume this will be 1 trace. Okay, 1 trace, 1 of these traces, this one, for example. And now we take periodic boundaries, which means this one will have to be hooked with this one will have to be hooked with this one will have to be hooked with this one, and now this one is the same as this one, right? And this is a trace, so this one is the same as this one, this one is the same as this one. Just to imagine things. And that's a scale, right? We contracted all 3 layers. That's a scale. Okay? And now this is the dimension of this is T, or T over 2 if you want. We have 1, 2, 3, 4 layers, is equal to 2, 2 half, 2 full layers. And then we will take this will be trace to the T, and then we will take trace to the minus T. So this will be composed of emission gate, emission conjugate gates. So it's like reflecting this picture in the mirror. Right? This is forward and backward evolution. But it is not like a correlation function. I remind you that this is like 2 disjoint objects, right? I mean, this is trace which is scalar by itself, and this is another trace which is scalar by itself. There's no observers here. This does not depend on observers. It's a pure object, right? No local observers. It's a global object. So sorry, I just have to finish this picture, but then we can really discuss the details of evaluating the picture. So, okay. 1, 2, 3, 4, that's done. Okay. Indices, now this one is hooked with this. This one, this is periodic boundaries, this one with this. This one with this. So there's this guys there. 1, 2, 3. Sorry. 1, 2, 3, 4. This one is with this. 1, 2, 3, 4, yes. Okay. This one is here. This one is there. I have to make sure I make hooks from all the three ends because these are going around vertically or horizontally. So now this guy coming, this guy is 1, this one is the same as here, and this one is the same as there. Okay. So the point is this one is connected to this one, also this one, this one is connected to that. Okay, but just have to imagine that these are basically partition sums on autologous, right? They're very boundary conditions. And then I have to take the expectation value of that thing. Big piece. And now what I will do, I will have to average. And so how I will average? I will average by introducing small local fields. Some colors. And I'll take, this is a trophy system, so all the gates are the same. Well, yeah. Let's say we can just slightly indicate the gates, color. get gates. And now we'll say, okay, now we can put, after each gate, we can put local fields. And this will be like small local fields. So like we put, I really don't want to write it before that's going to work. Yeah, I think I should stop. But maybe just give me 2 minutes. The point is now we have local fields, right, which are the same in all layers, but they can be different from place to place. So it's the same gate here as here. Let's say you just put a local field after each pull application. So that's how it is. After each pull application, you put a local field here and here. And then after, yeah. And of course, I will just use the same color below. And below you do the same after each application, so it's here and here. And then in the next guy, you take a different field here and here. And here and here. It's a random field, so you can take a different, take a disordered field, right? You take a disordered gate. So in each different, in the next side, I take independent gates, so that is right? But there are just 2 of them because they are just 2 layers in time. Okay? And so on and so forth. So we'll get another color on this topic. Yeah. And so what I will do now, I will see now that if I look at, this is the same guy, but this is independent the same guy. This is completely independent the same guy. So if I just take one column of this and name it as a transfer matrix, then I can average all these local fields independently, because this guy never appears again. This guy is random in space, but of course the same time. But if I go, now I try to evaluate this using the space direction. So that's why I'm advocating this space-time duality trick, because if I can evaluate this in the space direction, I can average over random fields. I take random fields to be able to define spectral form factor. Then I average over random fields, but I average them locally in space. Right? And now this becomes, I'm sorry, it's time. So this becomes a quantum channel. This becomes now, yeah, I'm really, I think. So what I want to say is this is a transfer matrix. So what I have now is really t to the power L, because this is system size L or L over 2. Right? No, it's L over 2, because I have to define 2 sublayers in space. And then I can take it to risk. And now T is a composition of 2 things. This is U tilde, right? So T is composition of U tilde star. And then I do it T times. And then I compose it with averaging. Let's call it averaging, some superoperator which averages for these guys. And then I take another one, which is the same but just shifted. Okay? And then there is the shift pi minus 1, and then I average again. Okay, so now I will stop now just to comment what this means. The point that if I have a dual unitary circuit, then this U tilde are also unitary, which means that this channel, this thing, that this transfer matrix, is a composition of a unitary, because the dual is also unitary. So this is a unitary circuit in the space direction. So it's a composition of a unitary circuit in the space direction with averaging over random field. And averaging over random field is like averaging over a unitary channel. And averaging over a unitary channel is a channel itself. So altogether, this is a big channel in space of T qubits, or 2 T qubits. This is the brown and this is the red. So this is the channel in the 2 T qubits. And so what I have to look at now is to understand how many trivial eigenvalues this channel has. Because now I have to show that this channel can have eigenvalue 1, but there will be more than 1 of those. And then the rest of the spectrum is gapped away from 1 by a finite gap. Once I show that, then this in the limit L to infinity, thermodynamic limit, converges to number multiplicity of eigenvalue 1, which is precisely T. And the fact that this multiplicity is T simply follows from the symmetry of this quantum channel, which is translation symmetry in time, which is now translation symmetry in space, because time is the new space. Right? So we have a quantum channel which is translation invariant, so it has a symmetry, it has another charge, which is momentum, the space momentum, or the time momentum, which is the frequency. So you can explore this charge to show that there are P sectors, and each sector has a unique state. But there are P sectors, so multiplicity of trivial eigenvalues T. Now this is the end. I have to apologize for not being able to explain well what I mean at the end, but maybe just to get a flavor of why this is exciting. You see, I mean, the formulation is kind of nice and compact, but of course the still is kind of very hard and interesting is really to prove first of all the gap of this channel, and second, to show that there is no other eigenoperator. So the symmetry is nice, and symmetry really gives you that there is at least T trivial eigenvalues, but there could be more than T trivial eigenvalues. And to show that there are no more is it's a hard exercise. So I think I have to stop. So thank you for your attention. Yes.
Questions? Yes.
Yeah.
Could you just quickly tell me what the symbol before the field average is?
Before
Before the last field average, what do you write there? So the
before the what?
last field average, where
Field average.
the circle with the
This one.
yeah.
Yeah, this is pi to minus 1. It's a translation.
What do you want?
Pi to minus 1. Pi. So I used to letter pi. It's a periodic translation. It's a periodic shift. You see, I have these guys, which is just tensor product, and these guys are shifted by 1.
So that the large pi.
Yeah, these are the 4 pieces. You see, these are the 4 pieces that you have got. This is util that tensor t times, tensor util that has times are 2 replicas. Then there's the averaging, which couples the 2 replicas, and then there is this guy with the shift, and this shift is just meaning that we have to shift by 1. Of course, I cannot be precise now, but just the picture has more. Okay, so yeah.
Other questions?